the first question, the seasons are caused by the distance from the Earth to the Sun. Is that true or false? And actually, the answer to that we'll get to in this lecture. I'm going to leave you in suspense for the moment. But most of you are saying that the seasons are not caused by the distance from the Earth to the Sun. So we'll just remember that. The next sort of teaser is water spirals down the drain in the opposite direction in the southern hemisphere from in the northern hemisphere is what I mean here. So do we think that is true or do we think it is false? It's like public opinion is forming here. Okay, so we've been spending the last couple of weeks, as I've said to you a couple of times now, sort of dissing the layer model by adding things that are important in the real world that are missed in the layer model. And so the first thing that we added for about a week that was, I forget, chapter 3, I guess, was real greenhouse gases. Which are selective about absorbing IR light. And of course, if it can absorb, it can emit. Kirchhoff's law, it's always a two-way street. So the layer model, the original one, the pane of glass did everything. Greenhouse gases are choosier than that. And then the second thing that we talked about in the last couple of lectures was the vertical temperature profile is determined by what we call moist convection. So convection is where you heat it at the bottom and so it becomes unstable and turns over like a lava lamp. And if there were just gases in the atmosphere with no water vapor, there would be cooling as the gases rose up because they expand. When they expand, they just naturally cool off. It's because you're sapping some of the heat energy of the gas and turning it into the expansion, essentially. So you expand it and it cools down. You compress it, it warms up. It's a property of gases. But then we had to modify that by adding the effect of water vapor. So water goes to the liquid form and gives off a lot of heat when it does that. Or if you want to make steam from the liquid, it takes a lot of heat to do that. I'm going to leave this down. I'm going to use the screen a couple more times today. So I'm going to leave the screen down. Is that going to be OK for you all? I'll try not to write too far off. Can you cope? OK. So when the gas rises up and expands and cools down, the water vapor that it had becomes unhappy being water vapor. It wants to be liquid water. So it condenses. That's where clouds come from. And when it condenses, it gives off a lot of heat. So this is actually the engine that drives hurricanes. You have the air kind of over the ocean comes together in the center of the hurricane, and it rises up. And as it does, all of this heat energy from the water vapor comes out, and it makes the air in the center, or maybe in the eye wall around the center, rise up like crazy. So that's what sort of drives a hurricane. So when a hurricane is over water, it's continually getting more water vapor, which sort of drives the power of it. When it goes over land, it starts to sort of die out because it doesn't have the water vapor to sort of drive it anymore. So those are the two things that we've done. about how we would fix up a real climate model as opposed to the layer model. And now we're going to talk about the third, which is that the layer model assumes that the energy in balances the energy out. Sort of on a planetary average and on a long time, that's true because the Earth is very old and you can't just keep heating it forever. Ultimately, the books have to balance. But locally and locally and over time, energy in does not balance energy out. So on an average, and if you wait long enough, the books have to balance, but things are way out of whack in terms of energy fluxes if you just take a snapshot at one place or one time. So we're going to talk a little bit about that today and what that means for climate models. So the first most obvious example of, or one example of how energy is sort of not in balance is just the day and night cycle. So at nighttime, there's no energy, no sunlight at night. So the energy in is equal to 0. And so that's a lot like the question you did in the labs about what temperature is the dark side of the moon. If you want to balance the energy out equals 0, then the only way to do that if the energy out is sigma t to the fourth is to have the temperature 0. So what you calculated was that the temperature of the dark side of the moon ought to be absolute 0. And that's not exactly true. There is actually, the whole universe has some black body radiation temperature of a few degrees Kelvin that's sort of left over from the Big Bang that's bathing everything. So you don't actually find absolute 0 probably, but pretty close. The same thing would happen on the dark side of the Earth if you had to balance the energy sort of locally. So the nights would be much, much, much colder, and the days would be much hotter if you insisted that everything always be balanced right away, you know, all the time. So we got to relax that requirement if we're going to, you know, explain the way things work in the real world. And then, of course, there are the seasons, which are caused, as most of you correctly guessed from the iClicker question, are caused by the tilt of the Earth. Axis of rotation. So the orbit of the Earth around the Sun is not exactly a circle. So there are times when the Earth is closer or farther from the Sun. Actually, the orbit of the Earth around the Sun is something like an ellipse. So we'll draw it sort of exaggerated and sort of. So there are times when the Earth is closer to the Sun and when it's farther from the Sun. There is also a tilt of the Earth's axis of rotation. So if we draw the Earth and then a line through it, which is the north and south poles, actually the way the Earth is configured around the Sun now is that the Earth is closest to the Sun when the northern hemisphere, when the North Pole is tilted away from the Sun. So here we are kind of right there, and we're going around and around this thing, and the days are shorter and we get less sunlight, a lot less sunlight, because the days are shorter and because it's sort of a more oblique angle of the sun to the surface of the Earth up here when the tilt is going away like that. So this is the northern hemisphere winter, actually. It turns out that the Earth is closest to the sun when we have winter. And in the summertime, for us, the Earth happens to be the farthest away from the sun, almost. It's not exactly, but it's pretty close to the farthest away in the summer, in the middle of the summer, and closest in the middle of winter. So actually, the distance from the Earth to the sun goes the other way to make the seasons. And you can also imagine that if it was the distance from the Earth to the sun that controls the seasons, it would be summer for both hemispheres at the same time when you're close, and then winter for both hemispheres at the same time when you're far away, which is not how it is. The seasons are the opposite in Australia than they are here. So December, they never have a white Christmas in Australia. It's always summertime. Yes?
So the amount of visible light going into the L,
yes.
probably there before,
Yeah.
Does that change at all depending on how close the Earth is to the sun? Or?
Yes, it does. It does, definitely. So when the Earth is closer to the sun, the total amount of sunlight energy that you're getting is a little higher, per day. And that probably makes the northern hemisphere summer less cold than it would be if it was the other way around. So the seasons might be most intense in the southern hemisphere because they're close to the sun in their summer and they're farther from the sun in the winter. And so the way the Earth's orbit sort of changes with time sort of rearranges the intensity of the seasons a bit for just exactly that reason. But the tilt of the Earth's axis of rotation is what really causes the summer and winter. So there was some science literacy test that they gave to undergraduates at Harvard University some years back I read about, and most of them got this question wrong, and you got it right, so that's way awesome. Hear that? It's awesome. Okay, so at any given instant in time, the energy in and out don't balance in some local place. And so we have to sort of think about the layer model as being an average over the whole season and over the days and nights. But even if you do that, even if you take the annual average of the sunlight coming in at some spot and leaving at some spot, even so, locally, those energy fluxes won't balance in the real world. And that is, so how they look, if we make a plot of the energy flux as a function of latitude, the energy, so this is the equator. Here's the North Pole and the South Pole, or we could do it, South Pole, North Pole, so it's all the same. And the energy coming in is most intense at the equator, and it drops off quite a bit when you get into the higher latitudes. So if the axis of rotation was exactly, perpendicular to the plane of the orbit, if there were no tilt, then there would be zero radiation that you get in the north and south. So actually I read about a crater on one of the poles of Mercury. Mercury is the closest planet to the sun, fiendishly hot in the summertime. But this crater it's got a ridge kind of around it, so the sun never shines down there. And so the temperature right in this crater is just wicked cold because there's no way to sort of carry heat around on an airless, waterless planet like Mercury. But on Earth, we have the atmosphere and the oceans that can carry a lot of heat around. And as a result, so this is the incoming energy. The outgoing energy, which is determined by the planet's temperature, is sort of smeared out like that. So if you had to balance the energy fluxes locally, it'd be much, much colder in the poles and much, much hotter in the high latitudes than it actually is. And that's because there is heat transport. Y'all that just came in, you may have a hard time seeing the board if you want to move over someplace else or something. I'm going to leave the screen down. Okay, thanks. So models to try to predict the effect of rising concentrations of greenhouse gases on Earth's climate have to deal with this. You can't rely on a layer model that just sort of takes an average of everything. If you really want to predict the climate change that to expect in Chicago or Australia or whatever, you gotta sort of resolve this, and so you gotta simulate it. You gotta put it in your model to see how it is controlled and what might change it. And so we have to start thinking about winds and currents just a little bit. And to do that, the way that the winds blow and the currents flow on Earth is determined by the fact that the Earth is rotating. So there is this effect, the Coriolis effect, which is kind of a fake effect. It's designed to make it convenient for us to look at a weather map and think about, a storm system, over Iowa that's going to clobber us in about an hour or whatever, without having to imagine what this whole thing is like on a rotating sphere, because that all gets really complicated. So an example of this is, we can see, is a merry-go-round. So let's say we have a merry-go-round and it's rotating, spinning around, but we're looking at it from above, and a kid throws a ball on the merry-go-round across it like that, and we're looking at it from above, so we're looking at it in a stationary frame, so not rotating, and the ball goes straight, just like Isaac Newton says it ought to, right? You push it in one direction and it keeps going in that direction unless it gets disturbed. So, the wind friction or something like that could change it. But, if you were just doing it simply, you throw it and it goes in a straight line. And that's kind of makes sense, at the foundations of the physics, that it just goes in a straight line. But when we're standing on the Earth, we don't want to think about it in a fixed frame. We want to think of it as if we were rotating. So the way this merry-go-round looks, if you're spinning around, is the two kids are on there and they're not moving because we got a camera now that's spinning along with the merry-go-round. And so this kid throws a ball toward the other kid, but by the time it gets to the other side, the kid is sort of here. So the kid is to the left of the ball. If we do this with a camera that's spinning around, how this will look is like that. So there's actually a movie of this. So, what we're looking at is we're looking down at a merry-go-round. It's kind of a grainy picture, but so there are these kids sitting on the thing, and it's going to be spinning around, and they're looking at it from above. And we're going to see it in both the stationary and the rotating frames. So there, now the camera is spinning around with the thing, and you see the ball seems to go sort of sideways. It goes to the side. It's not going in a straight line. It looks like it's curving. Actually, it is going in a straight line, but we're in this wacky framework of rotating with it. And so it looks like it's curving in that rotating frame. See, it just goes right to the side there. So if we want to write an equation for the motion of that ball, we have to add this sort of fudge factor called the Coriolis force. To make the equations of motion work in a rotating frame of reference. And so the way this works, we've got the motion of the ball, and it's going in some direction, and we want to at some time in the very near future have it be going that way, and then that way, and that way. We want it to rotate. It turns out that the force you have to apply to the ball to make it change its direction without changing its actual speed has always got to be at right angles. So this is motion. Has to be at right angles to the motion. So here's Coriolis. So if this force that you were applying to the ball pointed forward at all, it would make the ball accelerate. Or if it was going kind of backward at all, it would make the ball slow down. And neither of those is what we're really after. We just want it to turn without changing its speed. So the Coriolis force always has to be at 90 degrees to the direction of motion. And then which 90 degrees, whether it's this way or that way, depends on which way the thing is rotating. But so you can add this sort of fictitious force to Newton's laws of motion, and you can make everything kind of work the way it appears to if you're in a rotating frame. So now the world is spinning like a merry-go-round, but it's a little more complicated in that it is a sphere instead of a disk. So there's a sphere, and let's say it's rotating in this direction. And one way that you can sort of see or demonstrate the rotation of the Earth is with a device called a Foucault's pendulum. They have one of these at the Science Museum. They have them at various museums. They have to be really tall, so you need some like really tall atrium or something in a public space. And there has to be some kind of a very low friction swivel bearing up at the top, and then there's a big heavy looking weight at the bottom. So at the Science Museum it's this metal sphere, something like this. And you get this thing going, some employee of the museum gets it going in the morning, and it's going in some direction, and then as time goes on, it sort of changes its direction. So first it's going, looking at it from above like this, and then later it sort of spins its direction of swing. So you can set up a bunch of little things that get knocked over by the pendulum and have little markings on there to say, well, if these dominoes have been knocked over, it must be 11 o'clock or something like that. The thing spins because the Earth is rotating out from under it is what's happening. So if we take a Foucault pendulum like this as a sort of a rotation sensor, let's put one at the North Pole. Like that. And get it going. And it's rotating. It's in an inertial frame of the fixed stars. And the Earth is spinning. And so we get this thing going, and let's say it's going in a plane between sort of those two stars. The Earth spins under it, and so it appears that at the pole it rotates 360 degrees in 24 hours. How fast the Earth is rotating. So right at the North Pole or the South Pole, it's just like the merry-go-round. It's kind of, there's nothing tricky there. Now we're going to do one at the equator. Get this thing going, and we'll just have it rotating north and south. It's easier to visualize that way for me somehow. So we get the thing going north and south, so we do it at some time, and now the Earth is going to be spinning as time goes on, and so the direction, where down is going to change, but the pendulum is always going to face down because gravity is pulling it down. It doesn't sort of lift itself up, like levitate itself as the Earth turns at the equator because there's gravity always pulling it down. But the north-south axis of this, toward the North Star and the Southern Cross or whatever, there's no reason why the spinning of the Earth changes that. So up here, you spin it around, and the pendulum is free to change because the way that the Earth is spinning is kind of perpendicular to the way gravity is. So the pendulum can spin this way, but on the equator, it's always got to face the center, and the north-south doesn't change when you go around. So on the equator, there's actually no rotation. And in between, there is rotation, but slower than at the pole. And then in the southern hemisphere, rotation in the opposite direction. Does that make physical sense? Okay, so the Earth is going in this direction, say, so this pendulum is going to appear, let's see, let me get this right. So the sun rises in the east and sets in the west. So yeah, I think I had this right. So if we were here, we'd see the sun rising in the east as we come around. Okay, so now the pendulum is going to be going looking down. The pendulum is going to be rotating in a direction, apparently, clockwise looking down. If we go to the South Pole now, we're looking at it from the other direction, and so looking up at it, it's spinning the opposite direction, and so the pendulum is going to go in a counterclockwise direction. Does that make sense? Well, I'll take that as a qualified yes. Okay. Anybody else not willing to take my word for it? Talk about it. So there's this rotation that affects the motion of things, currents, thrown baseballs, whatever, on the Earth because the Earth is rotating. It's more tricky than a merry-go-round because a merry-go-round is just flat. But at the poles, it's just like the merry-go-round. At the equator, there's no rotation. And in the mid-latitudes, it sort of goes from 0 to the strongest clockwise, and then to 0, and then the strongest counterclockwise at the South Pole. So it's a little more complicated than the merry-go-round, but it's the same kind of idea. So what does this do to winds and currents? The bottom line, the end result, is a phenomenon known as geostrophic motion. So let's say we're going to make some current flow in water, and we're going to do that by having some sort of a push in some direction, like wind. Say the wind is blowing in some direction, and it's pushing water to flow in that direction. So there's like friction between the air and the water. So the current, when you first start doing this, goes the direction you push it. It makes good sense. It goes the way you're pushing it. And so the current starts to move, and anything that's moving starts to incur this Coriolis effect. So the Coriolis effect starts to affect the way, the balance of forces in that moving water. So the Coriolis is always 90 degrees to the direction of motion. It's to the right in the northern hemisphere, to the left in the southern hemisphere. So that begins to act as the current starts to flow. And what it does is the same as what it does to the ball on the merry-go-round. It starts to make it, deflect the motion to the side. It doesn't change the speed. It just changes the direction. That's because it's 90 degrees. So after a while, so this is initially. And then after a while, I'm going to say the wind is still going the same direction. The current has sort of spun around to the right a little bit because of the Coriolis. And as it spins to the right, the Coriolis always stays at 90 degrees to the right of where it spins. So there's Coriolis. The Coriolis is still acting on the current, and it's still twisting the velocity of the current until eventually you end up with an equilibrium where stuff sort of stops changing, and that is where the Coriolis just balances the push from the winds. And the way you do that is by having the current winding up, going 90 degrees to the right of how you're pushing it. So it's this weird counterintuitive result, an astonishing result, that you blow it this way and it goes sideways on a rotating planet. It doesn't do it immediately. It takes enough time for the Earth, to feel the rotation of the Earth. So it takes time for, what's causing the current actually to rotate like this is not Mr. Coriolis. We just made him up to make our math easy. What's making the current rotate is the rotation of the Earth, and so it doesn't rotate instantly. It takes, a couple of days before it rotates enough that it's going 90 degrees to the right of where you're pushing it, and the Coriolis now is just balancing the push from the wind. So it's sort of like you know, in equilibrium where things aren't changing anymore, you want everything to sort of balance up to zero. So the push from the wind is just being counteracted by the push back by the Coriolis. And when all that balances, then you have equilibrium. So it is as if, let's say we have a bunch of water in a bathtub. And instead of a wind force, we're going to make a push by changing the water level in the bathtub. So water level, high, water level on one side and low on the other. So maybe you've got a nephew or something with, you taking a bath, and he likes to go back and forth, and he gets the water sort of sloshing back and forth. And so, you know, in one of his wild swings, he's got all the water on one side of the bath, and what it wants to do is flow back. So it's got this push from the high water level to the low water level, which is the same, has the same kind of impact as the push from winds, but you know, it's now from pressure actually, because down here there's a higher pressure because the water level is deeper than down here. So, you know, it's this push force due to the pressure from the weight of the water, actually, in this case. But if you've ever given a bath to your nephew and he's done this, you know that the water doesn't flow sideways. What I'm telling you here, if you're willing to let me get away with this, is that in geostrophic flows, the motion of this water, the push force is this way, but the actual motion of the water is coming out from the board. The water is flowing sideways from the direction that you're pushing it. Doesn't happen in a bathtub because the water sloshes back to the other side, you know, in 2 seconds or something like that. It doesn't have time to feel the Earth's rotation in that amount of time. But in the ocean, there are currents like the Gulf Stream, and they actually have, so the Gulf Stream is sort of flowing northward. So here's the US, there's Florida, Cuba, the Gulf Stream is sort of flowing along the coast and then sort of northward toward kind of Norway and all of that in the ocean. And it turns out that there is higher water level on one side of this current than the other, like by about a meter, this much water. There's that much more water height on one side of that flow than on the other. So there's a push force going from the high to the low, and you know, if you just set this up and then let it happen instantly and didn't give it time to sort of feel the Earth's rotation and come to equilibrium, it would just go from the high pressure to the low pressure like in the bathtub. But the Gulf Stream has been there for many, many days, many, you know, thousands of years even. And so it knows about the Earth's rotation. And so the direction of flow, did I get this wrong? Oh my God. I did. We want the Gulf Stream to go this way, so that means the push force has to be in this direction. Push force is in this direction from the high water level to the low water level. The motion is in 90 degrees to the right. Coriolis force is going against the push force, and so that's the equilibrium. So if you ever look at a hurricane or a storm system or something like that on a weather map, this is what you see. A storm system has got at its center low pressure. So Now we're talking about gas pressure like we've been talking about before, the force of molecules bouncing off of you know, whatever you're measuring the pressure with. You have low pressure in the center and then high pressure all the way around. The natural way for gas to flow would be from high pressure to low pressure. It would be like the water in the bathtub would go from where it's deep to where it's shallow. It's exactly the same. And so you would expect there's a push force like that. But it doesn't do that because the storm is around for a long period of time, long enough to feel the Earth's rotation. And so what you end up with is motion that goes 90 degrees to the right of that in the northern hemisphere. And so you end up with these cells, these circulation cells that go around these low pressure systems that are storms. So if you were to think of this as some sort of a landscape, say, some like a sheet of rubber or something, and you push it down here so it kind of has this this dip in it, and then put a marble on it, you would expect the marble to just go down there to the center, but it's as if the marble doesn't do that. It just goes around and around and around this hole. And so a low pressure system like a storm lasts a lot longer on Earth than if Earth was not rotating. If it was not rotating, then it would just smooth out, just fill itself up, you know, like a hole in a tub of water. If you make a hole in the water, it would just come back quickly. But because the flow tends to be sideways to how you're pushing it, you get this thing that goes around and around, and it's much slower at sort of filling up the hole. So the great red spot on Jupiter is another example of something like this, and that's been going for hundreds of years, and you know, might be continuing on for hundreds of years into the future. So if we were to make a hole in the atmosphere like this, or a hole in water, and just instantly see what happens, it doesn't feel the Earth's rotation. It's sort of analogous to a top. So a top spinning around, and it stays up almost sort of by magic, it seems like, right? And it starts to tip, but if it tips, the rotation sort of catches it. But if the rotation was so slow that it could completely tip over before it had a chance to feel the rotation, it would be essentially not rotating. It would be like trying to stand a top on its pointy part without getting it spinning. It would fall over. It would fall over instantly. It wouldn't feel the Earth's rotation. So the answer to the second eye clicker question is false. Let me just bring it up again so we can see the question. Water spirals down the drain in the opposite direction in the southern hemisphere. So we've got some sink, and we just let the water go down the drain, and it starts to spiral when it gets there. If you had a really, really big sink, and it took, you know, a week to drain, then it would feel the Earth's rotation, and it would go according. You could use it as a hemisphere detector. Are you in the north or the southern hemisphere? But for a real sink, a bathtub or toilet or whatever, it happens so fast that it doesn't have a chance to feel the Earth's rotation, and so it does not flow in the opposite direction in the southern hemisphere. Is the sort of dogmatic answer to that one. You can believe me or not, but that's what I will tell you. Okay, so last thing. In order to make a climate model to really predict what will happen with global warming, a new model has to have the heat transport And so that means winds and currents. And that means we got to have this geostrophic motion. So the models that they use are very similar to the kinds of models they use to make weather forecasts. They are on a grid. So you've got like a checkerboard. You divide the world up into squares. And in each square, there's some sort of push force. So, you know, maybe there's higher pressure in this box and this box. And so there's a pressure force. And there are, you know, temperatures and cloudiness and the wind speeds from the last time step. And you have to take these time steps. So these calculations are, I mean, the codes themselves are pretty simple. It's much more simple than, say, a copy of Microsoft Word or something like that, which probably has 10 times the number of lines of code to make it work as one of these climate models. But it takes, you know, it can take weeks or months to do a long spin-up of one of these models. And the reason why it's so expensive, let's imagine if we were to double the number of grid spaces in each dimension, so doubling the resolution, doubling the detail of the model, that means we have a factor of 8 increase in the amount of math we have to do. Plus, as you make the grid points smaller, the time step has to be smaller. So overall, it runs something like 16 times slower if you double the detail in the models. And that's what we're sort of up against in trying to do these climate models. But nevertheless, you can see in this figure here from a climate science assessment report changes in the sort of level of detail in these models. So the first assessment report came out in 1990, I believe. And so the world in that model, in those models, sort of looked like that, a pretty crude checkerboard. The second assessment report had grid spacing of 250 kilometers. The third and the fourth one just came out in 2007. And there it is. You can see each one of those is something like a factor of 2 increase in the resolution, which requires about a factor of 16 increase in the computer power to make it work. So climate scientists are always going to be hungry for more computer power. We're never going to be happy. Okay, so we'll see you on Friday.